Well,
So sorry.
I consider
Excuse me.
I consider it an honor.
I didn't realize it. Okay, such beginnings are nice. At least everybody's awake now. Okay, so a few words I would like to say about George Sturman. He finished his undergraduate at University of Chicago, and his PhD is from Maryland in '74. He joined State University of New York at Stony Brook in '79, which was lucky because that's the time I was looking for advisors. And he has been there since then. He is well known for his first became famous because of his paper on jet cross sections, jets from QCD with Weinberg. And since then, he has been working continuously, essentially, on various aspects of factorization theorems and resummation techniques, which are useful for establishing QCD as theory of strong interactions. He has received the J.J. Sakurai Prize in 2003, and I will read the citation from there. For developing concepts on techniques in QCD, such as infrared safety and factorizations of hard processes, which permitted precise quantitative predictions of experimental tests by establishing QCD as the theory of strong interactions. So his work has been crucial for various analysis that one does. He has been a fellow of American Physical Society. He has a book on quantum field theory, which is there in our library also. And he has another unique distinction, which I cannot resist saying, namely he has been advisor to 4 Indian physicists, namely Sunil Mukhi, Ashok Sen, myself, and Rahul Basu, who unfortunately is not with us today. Otherwise, there have been 4 of us. So with these few words, I would like to request Professor George Sturman to give his lecture.
Thank you, thank you. Well, so you can hear me? I'm not sure I can hear myself. Okay, so the lecture today, first I would like to thank the organizers and everyone for the invitation, for this opportunity to visit the Institute for Mathematical Sciences. It's a visit I've been intending to make many times, and I'm glad that I had the opportunity to do so. It's a bit of a bittersweet occasion for me, and so in giving this lecture, I'm remembering my former student and your colleague and my friend Rahul Basu. So having said those words, let me talk a little bit about what I'd like to tie together some ideas of quantum field theory and some of the work that I've been involved in over the years with the Large Hadron Collider. So it's good. No, I don't want to do that. Does that show up? Oh, well. This is cosmic censorship or something like that. Let's see. Oh, no, that's, oh. Well, maybe if I keep going, it won't do that again. So we'll see how it goes. You can see there are 32 pages, so you can judge how I'm doing. So I'd like to cover from a particular viewpoint the kind of work that's being done at the Large Hadron Collider and how it connects historically and intellectually with theoretical physics through quantum field theory. So the basic idea is particle colliders and quantum fields. I'll talk specifically about gauge fields and the standard model, and then focus on quantum chromodynamics, or QCD, seeing and using QCD, and the role of classical analogies, which for various reasons I find appropriate to talk about this lecture. So this is a relatively short time. There are many fundamentals and historical landmarks that are left out. I won't talk about the parton model and all kinds of background like that. But it is an attempt to make a coordinated presentation. Now, as a further prologue, I could say at the beginning of this era, the era that we're entering now for the Large Hadron Collider was preceded by an era of what I would call the great standard model machines, LEP, the Tevatron, Hera at DAISY. machines had established the Standard Model, and before that was the real beginning of high-energy scattering. And here's a little quote from C.N. Yang back in 1969, before either Sham or I got to Stony Brook, but a conference on high-energy physics. Actually, this was a conference at which Feynman presented the parton model for one of the first times, and exists in a little book which is probably long since out of print. But it says, with the remarkable and characteristic foresight, it's clear that the increasing ability of experimental physicists to study quantitatively many particle final states is going to lead to a data explosion. And that became true in ways that could almost not be imagined then. A number of ideas and models have been introduced. These models are not always mutually exclusive, especially since most of them is not, none of them, rather, is completely precisely defined. And this is 1969, around not long after the establishment of this institute. And the world of particle physics has completely changed during that period of time as a result precisely of these experimental advances, which were just beginning at that time. Experimental and technological advances. So to establish a Standard Model, our methods indeed required better definition. And this talk describes a part of that story. And let me get rid of this little insect there. Okay. Whoop. No, you don't want to see that. Okay. Oh, you don't want to see that either. Okay. There we go. Okay. Page 3. See, this is 10%. What particle colliders do? So here's my only picture of the Large Hadron Collider from somewhere, you know, in the sky. I won't have any pictures of ATLAS or CMS, but you've seen them, I guess. Colliders, so what do? They prepare simple initial states, A plus B. So A is coming one way around this circle that's seen from the sky here, and B in the other. They're particles approaching each other. The detectors, of which we've all seen colorful pictures, observe complex final states, which I'll call Q, or actually later I'll call it F of Q. F just supposed to mean final. So A and B, the initial state has only 2 particles. F is some complicated combination of dozens of particles, even over 100. Each theory makes predictions on the likelihood of final states. That's what theories are supposed to do. These were the theories that Yang was referring to and said, well, none of them are really completely defined. But so here, there are different predictions associated with different theories. And the one that makes all the predictions correctly is the winner. Okay? So people went into this era with various candidates for victory. And we'll see how it is that we actually go about making these predictions, understanding these predictions, and relating them to what we see. What we try to calculate. So the basic measure of the probability to produce a final state, remember that was that F of Q or a Q, with Q, say, some energy exchange, something that's specifically, after all, if 2 particles come out in the same direction, that's not much of a collision. You probably won't learn much from it. Although there's plenty to learn about that if they transfer a little bit of momentum. But whatever the final state is, you have the relationship that the number of events, N of Q, is equal to a constant number. Well, it's not a constant. It's something that we can control, something called the luminosity, which is a measure of the number of collisions per unit area. And by that, the idea is the number of collisions per unit area, per unit time, integrated over time. So that's why people talk about integrated luminosity. This L here is an integrated luminosity. So that's something characteristic of the machine. But then we multiply it times a number which we call sigma of Q, or typically denote sigma of Q, which is called a cross-section. It's an effective area to produce some final state or energy exchange, which we're labeling by Q. So this little 3-element equation here with equals and times being sort of symbols, the experiments measure N of Q. That's what those big round things do. L is the accelerator scientists and the engineers and the technologists' role. The theorists, or theories, really, are supposed to predict sigma of Q. And that's how, given the different predictions, we can decide between the different theories. And what I'm hoping to do now is to discuss how we make those predictions first. So we'll talk about from quantum mechanics to cross-sections. So quantum mechanics is sigma of q. A cross-section is a transition probability to some final state f. So here f makes its appearance as a letter. Sigma of q is equal to some factors. The factors are then, again, geometrical. They have to do with the energy of the particles, and they have to do with pi, the volume of a sphere and things like that. But those factors are well known and standard and shared by all the theories. But what's characteristic of the theories that goes into getting this cross-section sigma of q is the absolute value squared of a quantum mechanical matrix element. And the matrix element is the matrix element which exactly corresponds to the two states. The state we put in, a plus b, at essentially t equals minus infinity, which probably means t equals several nanoseconds, as the particles begin to approach each other and they're focused into a collision point. So we have a plus b at t equals minus infinity, and then we take a quantum mechanical matrix element of that with a final state, which would be what is observed by a large detector sitting at one of those points around the ring, which actually I guess were labeled in the picture. So these amplitudes, whose absolute square we take, are a window to the micro world. Okay, how does that happen? Well, that happens in the most obvious way. That is to say, the most obvious way for which I guess most everybody here is familiar with more or less elementary quantum mechanics. Our states, which we hear in the Dirac notation, so it's a little bit more general than a single particle wave function, but the Dirac-Ket notation, the time derivative times IH bar on one of these states as a function of t is equal to h on t, which is a Hamiltonian, and that would be a part which is, I'm going to explain a little bit more later, k plus g times v. K, which we'll identify later in a rough sort of way as a kinetic energy, is also sometimes goes by the name of the free Hamiltonian. So K plus GV acting on the state gives us, that's the Hamiltonian acting on the state, gives us the time derivative of that state. So what we do is, here's a Schrodinger equation, well, we should solve it. And so the way that we solve it is by starting with the idea that these states A plus B, and far in the past and F far in the future, are basis states defined by the free operator K. Then we can solve for this time dependence by as an expansion in the potential term, which I'm labeling here. Whoops, no, that's not how I label it. Oh, okay. Every speaker should have an oscillation like that. It shows they're more interested in talking than they are in punching this thing. Anyway, so here we have G times V as this extra potential, which is going to mix the states for us. So what we're doing when we make predictions in this particular approach is that we're simply solving the Schrodinger equation. So then we get an expansion in G, and this expansion, as we'll see a little bit more in just a second, is exactly the sum over what are called Fimon diagrams. Each vertex in the Fimon diagram, everyone I pretty much would look at this and say, oh, these are, whoops, no? Okay, these are two electrons which exchange a photon, so that's a Fimon diagram for that. And it's second order in the particular coupling G, which goes by the name of the electric charge in this case. So here's that same diagram again. And the magic of Fimon diagrams is that actually they are, although there are many of them, they are quite efficient way of incorporating another way of looking at quantum mechanics, which is a sum over histories. So here we have a single Fimon diagram, which the photon's kind of democratically going in a vertical sense. So there's some sense of a beginning state. Our A plus B would be on. Oh, I really must stop this. A plus B is over here on the left, and in this case, F also equals A plus B on the right. And so what's happened is there's an exchange of momentum by the exchange of a photon. So each power of v, however, changes the particle content of the state. So the sum over Fimon diagrams is the sum of histories, all the ways of getting from state A plus B to state F. And in this particular case, on the left, we see the particle on top emits a photon, and so it's taken the system from a 2-particle state to a 3-particle state. So indeed, V, which is the action of this vertex here, has changed the particle content. The photon is absorbed on the other side by the lower particle, and again, the particle content changes from 3 particles to 2. On the one on the right, it's just in the opposite order. Both of these orderings, in terms of 2 different histories, are contained in the single Fimon diagram on top. And they're done, and the reason why Fimon diagrams are so popular, sort of, is that they automatically include Lorentz invariants. Because this different ordering in times may appear different in different frames. Okay, so that's the idea. This is a general picture of how we're going to approach the calculation of this S matrix from which we get the cross sections, and then when we know the luminosity, we can say what the experiments will find for each final state. So different theories have different V's. And I've given an example here from quantum electrodynamics where this wavy line is supposed to be a photon, but of course other theories will have different ones. And hence different histories and therefore different predictions. Different S matrix elements. I don't think I called that the S matrix, but the amplitude there is the S matrix. And therefore different cross sections, therefore for the given luminosity, different numbers to be observed at the accelerator through the detectors. This approach, this iterative or series expansion of the Schrodinger equation, and you can consider it as just the regular old Schrodinger equation, even though it's applying to a system with many particle states whose particle number is changing, this is perturbation theory. Or, and when we talk about QCD, it will be perturbative QCD. It's not the only possible route to the S matrix, and we'll see in a little while that for QCD in particular, it has serious difficulties which we have to figure a way of getting around. But so far, the other routes to get to the S matrix typically require things like special kinematics, maybe a low energy, so you have a low energy effective theory, some goes by the name of chiral effective theory for quantum chromodynamics, or you may have to go to some special theories about which we heard yesterday in Ashok Sen's talk, conformal fields, fields which enjoy dualities with gravity theories. Those can and have been used actually to calculate S matrices, but so far not in the elements of the standard model. So that's something which is progress still to be made for the future. So having said that, let's learn a little bit more about how we get these V's, these potential terms. So what are the K's and V's like? Well, here we have an example, the classic, most classic example, which is quantum electrodynamics. Here we go, QED. And our QED has this rather complicated symbolic form. It has a form where, we keep doing that. Okay, maybe I'll just read it. Every time I reach for that thing, I change the page. All right, so it says LQCD, but it should say LQED. I knew I'd have, this is the first typo I've noticed, so I'm sure there'll be others. It has it shows a mathematical expression sandwiched between 2 fields, psi and psi bar, which psi bar is more or less the Hermitian conjugate of psi. And then it has some Dirac matrices and a derivative, a mass term. And then it has this field A mu, which is a vector field, in this particular case, the vector potential of quantum electrodynamics. And that particular field on the first term on the left there is multiplied times E, the electric charge. And then there's another term associated with the Maxwell Lagrangian, d mu, or f mu nu squared, or d mu a nu minus d mu a mu. So this hidden in here, in this, is the E squared minus B squared, which is the Lagrangian of Maxwell theory. So it's a 4-component field, spinor field psi, and I'll just note something we'll come back to in a little while. When we set this mass, which as you can see, this is the danger of tech. You copy things over, and then there's kind of penetration depth of the old ideas into the new ones. So it says MQ, but it really means ME, or it means just M. So for M equals 0, what we're going to do is we're going to remind ourselves, or at least accept, if it's just a matter of taking it on faith, that these fields psi can be thought of as a sum of left and right-handed spins. And these are spins which are in relation to whatever direction the particles described by this field are moving. So right-handed, the spin is sort of like this, and left-handed is like that when the particle's moving this way. So we'll come back to that later when we really talk about the details of the standard model. But to interpret this Lagrangian in terms of the language that we gave before, to relate it to the underlying Schrodinger equation, we will have a two-line outline of quantum mechanics. Okay, so the first line is semester 1. The second line is semester 2. So the first line says you start with a classical Lagrangian. L is equal to a K, a kinetic energy, minus V, a potential energy. And then by a transform, you discover that the Hamiltonian is K plus V. Again, this is just for the simplest systems, but it works just fine for, well, with a little work, it works for quantum electrodynamics. And from this Hamiltonian, you determine what the eigenstates are, labeled here by n, and various other operators, which you can take commutation relations with the Hamiltonian with. And from that, you get expectation values of various physical quantities of interest, and you can relate them to classical measurements through the correspondence principle, which we'll also come back to. Now, K, this kinetic energy, actually will specify the basis of states, at least the ones we're going to use in perturbation theory. It's basically just a list of particles. The states themselves are just lists of particles and momenta, and in the case of spinors and vector particles, they're spins, left-handed, right-handed for mass equals 0. So what we have here then in our QED Lagrangian is a fermionic part here, which is, say, an F bar F. In this case, psi has just been denoted F. And this little part, the derivative in the mass. These play the role of K, and they determine the kinds of particles you get in the free theory, what their momenta are, how they're related to the mass, and to their spin. And then K for the vectors is just roughly, in this notation, is just given by the Maxwell Lagrangian. And both of these are quadratic in the fields. Here, F bar, here just A squared. And quadratic in the fields, we expect to get equations of motion which are linear and which therefore obey the superposition principle, which is the classical analog of saying that the system is free and particle number doesn't change with time. To get a change in particle number, you need this potential V. Well, if we go on to V, here's the V, the kind of V that we have. V is cubic or higher order in fields. For example, it's the product of fermion F times its conjugate F bar and a vector A with coupling G, and you throw in one of these Dirac matrices and you've got the V for quantum electrodynamics, which gives that Fimon rule and that picture of the order G squared or order E squared histories that we showed in the first diagram. So if G, the coupling here, which multiplies this, which we can think of, at least for now, as just purely adjustable parameter, is small, we can write down a few diagrams and get a good prediction. And again, that's a prediction for the S matrix, A plus B to F. You square it, that times some factors gives you the cross-section, then you get predictions for the numbers that you will see in experiment. Now, okay, this is it. That's, in some sense, a completely unfair and extraordinarily simplified picture of quantum field theory, but yet it captures, I would submit, most of what's actually making this system of ideas work, and one which makes it worthwhile to build great big accelerators to do experiments. So 4 decades of this interplay between different theories and experiments has led to the standard model. Now, the standard model is based on gauge theories, of which the quantum electrodynamics is an example. But gauge theory is not just for QED, but for the strong electromagnetic and weak interactions. But what are gauge theories? So that's the next topic that I'd like to discuss. as a natural development, since we know where we're going. We have 40 plus years of experimental history to try to explain. Oh, yes, well, I was about to demonstrate gravity. However, I won't do that solely because gravity is not part of the standard model. Okay, gauge fields in quantum theory. So let's start, however, instead of, this is quantum theory, will be a very general discussion, but we'll start with a point particle. So let's think about one of those expectation values. That was the second line of our review, two-line review of quantum mechanics. So we can imagine, actually, what I had meant to have here was an expectation value, which is, would have had psi on both sides, so that's the second one. But anyway, let's assume this is the expectation value of the non-relativistic point particle, kinetic energy, K. Well, here's the expression for it. It's minus h bar squared over 2m, and then the integral d cubed k. Actually, I'm not so sure about this minus sign. It's psi star of x, d squared by dx squared psi of x. So it's just one dimension for now. Or, well, no, it could be, this could be nabla squared if it's d cubed x. Okay, so here's what we have. Maybe we integrate by parts. So we had a d by dx on psi and d by dx on psi star. So that's it. I mean, that's just what the formula is. And we get familiar with that very early in our study of quantum mechanics. And we even get the sign right for the exam. So from phase to gauge. So now we make an observation. The use of this observation not immediately clear, but it turns out nature seems to have read this book. This is a very famous feature of quantum mechanical expectation values is that they're insensitive to the phase of the wave function. You can take any wave function psi and multiply times e to the I alpha, where alpha is some real number, not complex in general, but a real number, and you don't change k because psi and psi star, the changes in psi and psi star cancel out. So this psi prime, which is equal to e to the I alpha psi, has the same expectation value of the kinetic energy, okay, and many other observables. But the kinetic energy is the one we're interested in right now. However, if alpha becomes x-dependent, so I write down alpha of x, then you change the phase. If you change the phase differently in different points in space, then you change the kinetic energy. You impose upon the particle a certain amount of momentum, and then you change its energy just because the phase is changing differently in different places. So one approach to that is to say, well, that's life. You know, we'll just settle for this phase independence with a constant phase. But the other is to generalize what we mean. Yep, there we go again. Oh, too far. Okay, to generalize what we mean by the kinetic energy and to introduce a new operator, k or k prime, which instead of derivatives has covariant derivatives. And here are our covariant derivatives. We've moved the size in, or the factors of I in from the outside, and we have d by dx plus a new variable which we'll call ai. So ai is a vector. And if we have this combination, the so-called covariant derivatives acting on psi and psi star, this combination is independent of a phase, even if that phase is x. It depends upon the position. And in fact, the time, if you do it right. It's independent if our vector field, which goes in this context by the name of the gauge field, changes as a prime is equal to a plus the gradient of this function of the x of alpha of x. Now, this combination in which we change not only the phase in an x-dependent way, but we make a corresponding change to this new field, the vector field, has a kinetic energy which is independent of the phase that we choose. And this is described as a local symmetry in the case here of electrodynamics. So this was known really for quite a while by recognized in one way and another by Weil and also by Schrodinger in the 1920s. What was new, actually in 1969, it was still pretty new, and it was certainly unknown at that time that it would have much impact on the field of elementary particle physics, was the non-abelian generalization of this concept. So now what I'd like to do is give a slightly offbeat, well, maybe, picture of what this non-abelian generalization of the phase invariance that we just discussed means. We consider two different particle species which have the same mass and are otherwise completely indistinguishable, except that it is declared that there are two of them. So we say there are two wave functions, psi1 and psi2, which describe particles which are, indistinguishable. Now, what Yang and Mills said was, well, actually, in that system of two wave functions, there is another symmetry. And that symmetry mixes the wave functions. Doesn't only change the phase of one of the wave functions, or both of them independently, but actually turns the one into the other. And it would do that through this kind of relationship. Our psi prime now has an index j. J runs from 1 to 2. And in terms of our original wave function, psi1 and psi2, we multiply by the exponential of some matrix M. And if M is actually, the way I've written it isn't quite right. M should be anti-unitary. I've written it as e to the I times M. No. Yes. No, M should be Hermitian. No wonder I got confused. OK, so, well, e to the Im is unitary. OK, you knew. All right. So if e to the Im is unitary, then the total kinetic energy, k1 plus k2, is equal to the kinetic energy of these two wave functions combined. So the unitary matrices obviously implies that we have group theory. And we can't distinguish, however, because of this, at least using the kinetic energy, and indeed anything else in the theory that has this symmetry built in, we simply cannot distinguish directions in this psi1 and psi2 space. It's like navigating on some sphere. If there had been psi1 and psi2, you could imagine it being isomorphic to the surface of a sphere or something like that. But you don't know. There's no north pole on the sphere, no equator, no south pole. Your position on the sphere is completely a matter of definition. It's a puzzling kind of symmetry. It's trivial, but on the other hand, puzzling. Well, could nature make such a symmetry, which is an obvious generalization of the phase invariance, local? Yes. The covariant derivative, defined appropriately, still defines a gauge invariant matrix k hat for a Yang-Mills field. Now the vector field becomes a Yang-Mills field, and the Yang-Mills field in this language is a matrix, A, that transforms according to this particular set of rules. So A is multiplied by this unitary matrix on one side, its inverse on the other, but then you have to add an inhomogeneous term coming from the derivative of your matrix times the inverse of the matrix. And then if you say, oh, suppose I just really wanted to go back to the phase, in the case where M is just a number, rather than being a 2 by 2 matrix, or n by n matrix, then this reduces to the old gauge transformation. So a typical Yang-Mills locally invariant Lagrangian in field theory is given in green here. It looks just like quantum electrodynamics, except that now, instead of having one field, there's now a sum over n fields. N was 2 in the example we were thinking of a moment, but clearly it immediately generalizes to be having n fields. And here that phi is a Tech fossil. Okay? So now it turns out, now this was an idea actually that Yang-Mills, we are told by reading Yang's memoirs, that the idea was a long-standing one. What was difficult was not the covariant derivative. That was easy. And we can see it right here in essentially this set of equations, but rather discovering what this generalization of the F's had to be. And as is famously the case, the F in the Yang-Mills theories is a generalization of electric and magnetic fields. And it includes a potential, this potential here, with a cubed and a to the fourth terms, which typically go by the name vector self-couplings. So what happens now when we infer in general, as we go on from the abelian, the single phase invariance, and this non-abelian phase invariance, is that we've blurred the distinction between the kinetic term and the potential term, because it's only the combination of the two actually that has the symmetries which we're demanding to be built into the system. So there's something profoundly different about this kind of a theory compared to the simple picture which I gave earlier. Well, Okay. The entire standard model of elementary particle physics, fast forward, let's say to the latest LHC data, consists of what I would call the such proliferated fermions and related gauge fields. It's not usually written this way. Normally what we get is that particle data group little table or something that looks like a Rubik's Cube or so. But let's think about it this way for a minute. First of all, we start with the quarks. Each quark, when we talk about it, U, D, S, T, sort of assuming you can remember the letters even if I can't, each has 3 utterly indistinguishable massless spinor fields. And that's where this n equals 3 comes from in the standard model. These are the color fields. Then the left-handed spins in each of these, by now 3 fields, is again duplicated. That's where the n equals 2 comes from. And that will be the basis of the V minus A of the standard model. V minus A indicating that there's a coupling that will have a gauge symmetry only for the left-handed parts of these 3 fields for each quark. The leptons don't have these 3, this triplification, what do you call it? Tripling. They don't have this tripling. They only have their left-handed spins are each duplicated. So that's the same n equal 2. The gluons are a traceless 3×3 matrix of vector fields that are introduced to preserve the local n equals 3 gauge invariance. And the electroweak bosons are, again, a traceless 2×2 matrix to preserve local gauge invariance, but only when their spin is left-handed for both quarks and gluons. So that's our SU2 left. And there's another vector boson for good measure, which is U1. We put that one in so we can have a photon, but of course it's only part of the photon. Finally, okay, so this is the whole thing. Finally, there's a single complex scalar field in the standard model whose potential is chosen to force it into a frozen modulus in phase. And this is what goes by the name of the Higgs mechanism. This constant ground state shifts the potential V, some of the potential terms, to kinetic terms. Remember, I don't think well, okay, this is an example of how gauge theories can mix the kinetic and the potential and so blur the distinction between the two. So if you have something that goes like F bar F times this scalar field, and the scalar field has, in its ground state, is given primarily by a constant, then it looks just like the mass term that we saw in the case of quantum electrodynamics. So this shifts all potential terms to kinetic terms for all the quarks. It says for all the quarks and gluons, but I meant to say the quarks and leptons. Okay, this is read this gluons as leptons. And 3 of the 4 electroweak bosons, giving them all different masses, and in fact different ways in which they can interact with the electroweak vector bosons. Okay, so that's this what I would describe as the proliferation of fermion fields in the standard model. As if this weren't enough, then nature redoes these fields in triplicate again, now with different masses. And these are the generalizations, the difference between up, charm, top quarks, etc. So for this, the latter proliferation, there's no known gauge theory, at least not yet. Okay. So, moving right along, getting towards the halfway point. So I'll just make a few comments. I don't have a profound explanation of this. In fact, I don't know that a profound explanation exists. Well, but a few comments. Obviously, there's a complexity associated with this picture. This is an almost effusive number of fermion fields suggests some underlying principle, such as, without taking any credit or giving any credence to, proposed symmetries of complicated, compactified extra space-time dimensions, or space dimensions usually are the ones that are compactified. Now, on the other hand, it has a kind of simplicity. There are many fields, okay, because we really, really should think of these n equal 3 as 3 separate fields. We just can't tell them apart. And many parameters, but most of the parameters have to do with the way that the Higgs field couples and gives masses to the remaining to the leptons and the electroweak bosons. well, the leptons, the electroweak bosons, there really are no new parameters. So the basic parameters are just the coupling for SU3, the coupling for SU2, and the coupling for U1. So suffice it to say that now, okay, so that's the standard model. That's the gauge theories. That's the standard model. Now we remember we were trying to think about, well, why do we believe this on the basis of these collider experiments? Suffice it to say for now, as a complete oversimplification, that G and G prime, the couplings for SU2 left and for U1, are small enough that we can confidently compute the S matrix for electron scattering, electron-positron scattering, photons, W and Z production, and leptonic scattering, etc., and confirm SU2 left cross U1 from cross-sections in the manner that we described above, just through the simplest of the Fimon diagrams. Particle decays also provide paths to confirmation for the standard model, but which we can't follow here. So what we'll do is we'll follow the thread of the strong interactions and how collider physics has confirmed color SU3, the remaining part, the gauge theory of the standard model, including most of its most characteristic quantum consequence, which is asymptotic freedom. So I'll assume that the concept of confined quarks is something that pretty much everybody is comfortable with, so I won't go into how we know that. So for hadron colliders, the in states, that A plus B states we had at the beginning, are governed by the strong interactions which emerge from nuclear forces. The standard model candidate is quantum chromodynamics, of course. And of course, in the Lagrangian of quantum chromodynamics, only quarks and gluons appear, not protons, neutrons, or nuclei. So how can we do without them, all right? I'm not going to stand up here and tell you how QCD produces those things. Rather, we'll say, how could we confirm QCD in the context that we're talking about at colliders without completely solving the theory and finding all these good features? So QCD is the quark-gluon gauge theory. So there's, once again, in a simplified form, the Lagrangian, and a little bit about the history of where that came from. And we can think of L as being, think of it as being just a generalization of electromagnetic Lagrangian or Lagrange density with a kinematics associated with the kinetic energy of the electron, a piece that looks like the electromagnetic currents times the vector field, and then E squared minus B squared. So it's just a generalization of that, as we saw before. So as I indicated in the last transparency, the confirmation of QCD runs deeply through its quantum properties, which is sort of a surprise in a way, in the sense that the confirmation of SU2 cross U1 is almost at the classical level with quantum corrections. Here, you can't even get started without the quantum mechanics. So here, we're going to have to use the ideas of renormalization. So here's renormalization in a nutshell, a little bit longer than the two-line quantum mechanics, but still not so complicated. So the problem is here, we can define, if we like, the observed value of our coupling as we imagine we move, whoops, oh my goodness. Okay, we imagine here, if you look at the picture, you imagine a quark as emerging from the left and entering a ball, a three-dimensional ball, or four-dimensional ball of radius c times t. The quark's moving in very fast. And then inside that ball, the quark emits a gluon, and then both the gluon and the quark emerge from the ball. So c times t is a distance scale. And we imagine that we decide to define our coupling as the production of a gluon from a quark inside a ball of radius c times t. And we could do that for any t. Now, what we could try to do is look at the histories, or the Fimon diagrams that I've drawn there. We have the first one is the lowest order, but the second one is a vertex correction where there's for a while a state with an extra gluon inside this ball of radius ct, which, however, the extra gluon is reabsorbed. It may be reabsorbed by a quark, may be reabsorbed by a gluon. One of the quarks could have a so-called self-energy diagram here, also the gluon, as long as it all happens inside the ball. Now, if you sum over all those histories, you get infinity. And that infinity is simply this statement that there are too many states for the theory. The theory wants to populate states at very high energies, but it It simply can't come to a finite answer for that, for those kinds of processes or histories. So we sidestep this problem as follows. Instead of trying to compute the full amplitude by summing over all histories, we ask, how does the amplitude change when we change the radius of the ball? We change our definition of the of the coupling by saying, what's the probability for a quark and a gluon? Quark goes in, a quark and a gluon, this is not a black hole, quark and a gluon emerge after time, or with radius ct or radius ct prime, where t prime is close to t. Now this is a calculation which we can do, and from that we can get a differential equation for this coupling. G is a function of h, where h is Planck's constant divided by t, or if we wanted to measure it in units of energy, it would be h over t. And we can get d by dt of this quantity, and we can solve that equation simply assuming that we don't take t all the way to 0, but in fact we just do it in terms of its value at a particular value, which will identify this h over t with mu, a quantity mu of units of energy or of distance, depending upon how we do these, or inverse distance. And we define this g sub s squared over 4 pi to be the QCD fine structure constant. And here's the famous expression that we get, alpha divided by 1 plus b naught, alpha over 4 pi, the log of mu squared over mu naught squared. So the difficult part is just learning how to take this derivative, but it's just exactly what I said. Now what we notice about this is that as mu increases, this alpha of mu prime, or as mu prime, well, I didn't need the prime here, as mu increases, in terms of any given finite alpha s of mu naught, as mu increases, the alpha of mu decreases like the log of mu squared over mu naught squared times this constant. And of course, you can improve this by going to higher orders, but the qualitative result is the same. So this goes by the name of asymptotic freedom. And as you could see, it's completely a quantum mechanical process. It has to do with the fact that histories of the system are being explored even as the system goes through the most elementary of its processes, in this case, the emission of a gluon, the lowest order interaction or action of the potential. So we can use any mu we like so long as alpha s of mu is small. And we can do perturbation theory because this mu was just introduced as a definition of G. It wasn't something that forced us to go to a different theory. So what happens here, well, there are various physical interpretations of this. The colors of the gluons are lining up like magnets, and we describe this as anti-shielding. So but the bottom line of this is that radiation becomes weaker as the momentum scale increases. So Q could be a momentum transfer, and this, of course, aside from the typo, was the famous discovery of Gross, Wilczek, and Palliser, with Georgi playing a large role as well at a similar time. Near a quark at very, very short distances, or very, very high energies, the coupling is weak. On the other hand, as you go to longer distances, to the infrared limit, there's strong coupling, and immediately people said, maybe this is at least, if not an explanation for quark confinement, it shows that weak coupling and strong coupling can be consistent in the same theory. So far from a quark, coupling constant is strong. So asymptotic freedom opens the door to confinement at long distances, weak coupling at short distances, and the rest of this little story is to show how to use this. I guess I should ask when I actually started this talk. Does anybody remember? What? Oh. Oh, okay. So it's not as bad as it looks. All right, good. All right. So I'd like to say, as everybody recognizes, asymptotic freedom is a big deal, and I have this little equation here. Asymptotic freedom is to quantum chromodynamics a little bit like elliptical orbits is to Newtonian gravity. And so it's important, but it's the beginning of a story, not the end. For Newtonian gravity, people recognized immediately, I mean, within almost, archive-type timescales, that the three-body problem is qualitatively different and harder than the two-body problem. And for QCD, asymptotic freedom is far from enough. So we're posed with the problem of how to study a theory of confinement. Well, what's the ultimate goal? The ultimate goal is nuclear physics divided by QCD equals chemistry over QED, something along those lines. But how are we going to do this? How can we study the particles that give the currents that couple to the both to the gluons and also to the electroweak bosons? Study the particles that give the forces, the gluons, expanded in the number of gluons in perturbation theory. The basic problem we look at is QCD has confinement, so all observed hadrons are bound states, and bound state scattering involves complexity and strong forces when we try to define our asymptotic states, those A and B that we had before. So what do we mean by the S matrix in QCD? Does this make any sense at all? Well, of course, the story is I'll argue that it does, although it must be said that it was considered for a while that it was kind of a silly thing to look at. Okay, what the data tell us? Well, what the data tell us? Well, the data will, okay, so this, we're going to start out, we're just going to discuss a little bit what the data tell us. But first, we'll say the S matrix, even, as I just said, even at high energy is pretty hopeless in perturbation theory. So now suppose you start with some state A in and B out. I should have used other letters given the convention I was using before, but I think it's clear enough. What you get when you do perturbation theory is the natural scale is the momentum transfer. So I should choose mu equal to q. Well, then this log vanishes, so you don't have any problems with that, even when that log is big. But the problem is then you have the log of m over q. And m could be any of the scales in the problem. It could be hadronic scales, it could be a quark scale, it could even be the mass of the gluon, which is equal to 0. And so this log is minus infinity, at least in some way of looking at it. If you try to choose q equal to one of the mass scales, then you're faced with the log of the energy scale. So no choice of the renormalization scale is going to make these logs small and give us any confidence that we're going to be able to understand QCD at higher orders in perturbation theory. So you might say that from the perturbative point of view, we're forbidden to look inside the final state, not to mention the initial state. But still, could it be possible to see quarks and gluons? This is a question people couldn't happen but ask. Could a simple short distance process imprint itself on the eventual structure? So now, without going much into the theory, we'll just say, suppose it works. I mean, what should we look for? So for example, suppose we have the annihilation of an electron and a positron. Okay, this is supposed to be E and an E bar. I should have put a plus there. It would have been a little clearer. Anyway, so here we have electron-positron annihilation. There's another one of those quantum mechanical histories. And they annihilate perhaps to one of the electroweak vector bosons at the lower energies. It would almost always be an off-shell photon, which then would decay, among other things, it can decay into a quark of, say, flavor F. I'll just use F to be quarks typically in these pictures. So you can write that down at lowest order. It's an extremely simple picture. It's one you see in quantum electrodynamics. You could imagine it happening in quantum chromodynamics. You just are hesitant to do it because you then ask yourself, well, what happens out here? I mean, how does it become confined and all this other business? But you could still say, well, could it be that the real final states possibly look like something like this? Here we have the electron-positron coming in. Here are two quarks, a quark and an antiquark coming out. And could they translate into something where you get a bunch of hadrons, which carry most of the momentum in a direction which was the same direction that the quark pair came out? So way back in 1969, for E plus E minus goes to QQ bar, which is what we had before, Drell-Yan, pre-QCD, in fact, pretty much pre-recognition that gauge theory was likely to be the answer, assumed a transverse momentum cutoff of hadrons in the final state relative to the axis defined by the quark pair. And it was a prediction that said the flow of energy of hadrons would follow the angular distribution for the production of quarks. It's just a statement. You just say it. You say, well, how would that work? Oh, well, the hadrons are going in the same direction. So we'll say they have a PT cutoff. And the prediction for the quarks angular distribution, which is this little represented by the theta in the picture, is 1 plus cosine squared theta. That tells you it's spin 1/2. It had been spin 0 for the quarks, you'd have seen sine squared theta. So there's the quote, because of the cutoff, the distribution of secondaries will look like two jets. Okay? Now, jets actually is a word that had been around for a while. I mean, not just the airplanes, but it was known from cosmic ray physics before. But I don't know if they were thinking of that. Well, anyway, it was Physical Review D1. Somehow it was a good choice where to publish. So in this picture, partons are said, quarks are said to fragment into hadrons. So here actually was a question you could ask of nature. You could ask of nature right then, even before QCD had been invented, but later, QCD, you can ask it of the theory. Would the final states look like this? And in nature, they did. And here's the famous paper where it was first seen about 6 years later. This is not a picture from that experiment, but rather a picture from LEP, where we see two turquoise jets appearing, and these little colored boxes are the energy flow, which I referred to before. And indeed, energy flow is really the key to this whole thing. Well, it doesn't just happen when electron-positron annihilate into hadrons. It also happens when electrons scatter from quarks, say of flavor X, F. It appears that part of the momentum of this guy has disappeared in the production of the EPS file. Anyway, so this is a picture from Hera from a while back. You can see the scattered quark, which was coming in from the right. A proton was coming in from the right, and then a quark is scattered, and that's that big red spray. It also happens in hadron-hadron collisions. So in here is a typical example. A quark and an antiquark might annihilate into a gluon, which then produces two other gluons. And here we have a picture from the Tevatron in terms of energy flow, a so-called Lego plot. And here's a nice rolled-up Lego plot from CMS. And I think this is the highest energy jet they had seen to that time, something over 2 GeV on each side. It was really 2 TeV, rather, on each side. So from that, that's very nice. It certainly, before people had a theory for this, or just when the theory was that I'll describe in the closing slides, was being developed, people saw that this qualitative idea of looking at the lowest order quark production or gluon production and then simply translating that into the flow of hadrons was an idea that had some promise because there were hints of it in physics. Actually, I would say it wasn't until about 1984, almost 10 years later, after the E plus E minus experiments, that people really began to feel that jets were an indelible part of QCD collision theory when the SPS at CERN was built, and you started seeing jets of dozens and even 100 GeV. So what turned into quantitative physics, all this into quantitative physics, are two results which are summarized by the way of thinking about it is if we go back to that idea that in perturbation theory we're going to get logs of the momentum transfer divided by the masses of the particles. And both of these basic results are motivated by classical considerations so that they're not so difficult to explain. The first one goes by the name of infrared safety. And that's a statement in somewhat more technical language that these jet cross-sections that we just discussed before are calculable if the jets are defined by smooth functions of the flow of energy. And in this particular case, these logs of Q over M cancel in those cross-sections. And we can just calculate those sigma of Q's directly. The other basic property is factorization. In hadron-hadron collisions, jet and heavy particle productions, so for example the Higgs, these cross-sections are the perturbative scattering of quarks and gluons, which we can calculate, times universal functions called parton distributions. In this case, what happens is the logs of M are universal. They're still there. They don't cancel, but they can be grouped into the parton distributions. And what's left over will tell us how likely it is in terms of those distributions or in units of those distributions to produce heavy particles or to produce jets at various angles and various numbers and energies. So what I'll do is I'll just close with the classical inspirations for these results. So here's number one is jet cross-sections. And the basic idea behind this is pretty simple. The radiation of accelerated charges in the classical limit plus the correspondence principle tells you that there's always unresolvable soft photon radiation. Okay? And in 1939, Bloch and Nortzig showed the infrared finiteness of QED cross-sections, and only cross-sections. That's sum over soft photon emission, where you have some E gamma. You always have to include the possibility that there are photons that are emitted with an energy which is less than the momentum transfer. If you try to avoid or calculate the probability of finding a scattering process with no photons emitted, then what you will always find are logs of the mass of the electron, or more generally, the momentum transfer, divided by the mass of the photon. And that will give you it. But if you sum over all of these unobserved soft photons, so you include states in the cross-section that have an extra photon and those that don't have an extra photon, this infinite log, because this log is minus infinity in quantum electrodynamics, will be replaced by a log of 1 divided by this resolution parameter, epsilon. So that's going to be finite, unless epsilon's extremely small, like 1 over really small, okay, because alpha is like 1 over 137. So by analogy, at high energies, you have to also identify a different resolution problem, not just the emission of soft photons, but the emission of photons and gluons that are effectively parallel to the particles that emit them. So if you have two massless particles, one's moving along this way, and it decides to split into two massless particles moving exactly the same direction, each with half the energy, or one with 2/3 and one with 1/3, and so forth. If they are exactly collinear, you will never be able to tell the two apart, because the momentum will be flowing exactly the same way, and the charges, the total charge, is being conserved by this splitting, and the charge will be exactly the same. So you have an idea, a picture, which is something like this, which says that you should have, let's say in the production of, in this E plus E minus goes to Q bar, you should allow for soft gluon radiation in all directions with some resolution parameter epsilon, and then there's the possibility that you have, the necessity of summing over all the energy that flows out within some angular resolution, delta, where delta can be thought of as a small number. Now, there are many variations of this, but this is the basic idea. And here, what happens is that the logarithms which kept us from calculating in perturbation theory, which were of the form, say, alpha s times log squared a momentum transfer, which in this case might be the total invariant mass of this system, divided by the mass of the lightest particle around, in this case the gluon, are replaced by the logs of the inverse of these two resolutions. And this observation, this approach of calculating quantities that depend only on the flow of energy, goes by the name of infrared safety. Yes? 5 minutes, yeah, oh, okay. Oh, let's see. How am I doing? 27? Okay, we can get through the rest of this. Okay. Okay, so this is perfect for QCD. Asymptotic freedom gives that alpha s of Q decreases with Q, and for jet cross-sections, we can choose mu equal to Q and get a nice expansion, this alpha s of Q times numbers. And this gives this perhaps familiar picture of alpha s as a function of momentum transfer and plotted against the theory. And the whole idea is, for each cross-section, you get an expansion that looks like this, with just numbers here, times alpha s of mu, and if you measure this side, and you calculate these CNs to some approximation, you solve for alpha s of Q. And all the alpha s's you see are the result of such a simple algebraic solution. For the second picture factorization, I'll just say a few words. General cross-section, so for example, the production of a Higgs particle of mass m should be written as an integral of a calculable piece, as I said before, A partons A and B. Oh, my thumb is too big. Okay. Partons A and B going to the observed final state F plus some radiation that we, as usual, don't want to observe. So we sum over it times parton distributions, which are labeled here by phi's. And factorization proofs justify the universality. And what I'd just like to finish up with is a little work that long ago I did with Rahul Basu and Anubal Ramalho back around 1983. And just a couple of observations. It's, first of all, a classical argument. We actually did a calculation, but we made this classical observation, which is really quite standard. It comes right out of electromagnetism books, so I won't go into the details. Why a classical picture isn't far-fetched, it's the same as before. The correspondence principle is the key to infrared divergences, and so low energy, quanta, and the sources of all the logs of momentum transfers are masses divided by light masses. An accelerated charge must produce classical radiation. And an infinite number of soft gluons are required to make a classical field. So you have to sum over all of the quanta associated with the production of that classical field. And so what we found useful to look at was just simply to ask, what happens if you have a target particle? So you go to the rest frame of one of, say, the two hadrons in the Large Hadron Collider, and you look at what the fields associated with the other oncoming proton are. And what you can do is, first you can think, oh, what would it be if instead of a gauge theory, you had scalar theories? Well, what you'd see is that the field, the source field, goes down like 1 over r, is simply Lorentz contracted to a sheet for a scalar theory, just as much as for electrodynamics. Pretty much, since I'm running out of time, I'll just summarize. And what you find for a scalar theory is that the width of this sheet, this wall or shock wave, is in fact, it goes down like 1 over gamma, where gamma is the usual special relativity gamma. So your shock wave for a scalar field actually contracts like a ruler Now, you can then do the same thing for your gauge fields. A0, for example, is one of the components. Or for the field strengths, in this case in electrodynamics, E. And what you find is that the gauge theory is even better as far as the field strengths are concerned. Instead of being Lorentz contracted like E, or 1 over gamma, it goes like 1 over gamma squared. So it's really, really Lorentz contracted. And information about the oncoming proton does not arrive until the two literally overlap and the hard scattering is already occurring, and it's too late for soft particles to have any influence on it. So the history of the protons is indeed universal and completely independent until a time scale characteristic of the hard scattering. However, if you try to analyze it in terms of the vector bosons, what happens is that you end up with finding out that some of the gauge components don't actually Lorentz contract at all. Some of them even get larger as you boost the oncoming projectile. But those pieces that you see, they get larger, are in fact all entirely total derivatives. And we know just from our quantum electrodynamics that total derivatives don't give forces or field strengths. So the large part of A can be removed by a gauge transformation. And this is about the end of it. The force field is highly Lorentz contracted. It gives you, in fact, an estimate that we found of corrections to factorization, which is still accurate to this day. Non-factoring contributions are down not just by 1 over s, or 1 over q, where q squared, where q is the mass of the produced particle, but 1 over m to the 4th. This was one of the nice results that we found. Well, I won't go into all of the words here. I'll get to the last slide. With these methods, we have calculations, and here we see data. So this is the only data I'm actually showing in the last slide. From the Tevatron for jets up to as much as, what does it say, about 600 GeV. And then recent data from CMS, where data begins at 1,000 GeV, so a TeV, and goes up for dijet pair masses all the way to 4 TeV. So the tools for the coming era of understanding with a well-defined standard model with all the challenges and complexities it still presents us with will include those discussed here. Certainly among the current challenges is to estimate corrections as we decrease the resolution parameters. So those epsilon and deltas we saw before, or their more sophisticated equivalents For those and the experts, things like anti-KT and things and Aachen, Cambridge Aachen, and so forth. As you do that, your logarithms of these resolution parameters become larger, and you begin to get calculations where the strong coupling aspects of QCD become more important. So certainly a motivation is to explore fully the potential for new physics signals at the LHC data, if indeed they're hiding behind our ability to calculate at this point. And certainly the taming of this wilderness be one continuation in the development of gauge theories and of elementary particles in general. So thank you.
Thank you very much, George. For one additional reason that you did not demonstrate gravity.
What?
For one additional reason, I'm thinking you did not demonstrate gravity.
Yes. It's closer than I thought.
We have run out of time almost, so I will not take any questions now. However, I would like to announce also that George is giving a technical talk at 2:30, between 2:30 and 3:30 in Alladi Ramakrishna Hall today. So I think we can take questions to that because there is another talk coming now before the lunch. So let's thank the speaker again.
Oh, God. I didn't.